I can do this.
Okay. So, all right, screen share, yeah. Okay, this, can I just test this once?
Yes.
All right.
We can see.
You can see that stuff?
We can see it.
Okay, cool.
It works. Excellent. And maybe I have to edit some of this out. But anyway, again, so we have Dyan Glas, and he was kind enough to speak with us, the Houston Robotics Club, and for our first robot talks. And Mr. Glas, take it away. Introduce yourself, please.
Okay. Well, thanks a lot for inviting me to give this talk. It's pretty cool. I love sharing, my experiences with robotics, and I think like hobbyist robotics club type things is that's really where you see people's passions in robotics. So my background, well, I studied aerospace engineering originally at MIT, and went through a number of different routes. I taught English briefly in Japan and stuff. Ended up getting into social robotics, and I worked at ATR, which is a company in Japan that does a lot of academic research, and at Osaka University, which is where I got my PhD, both in Japan. And I was in Japan for almost 17 years doing that stuff. And the thing that really attracted me to Japan was that they have these, they have all these like social robots. So, instead of industrial robots or military robots and things, they have robots that, act as social peers. They go around and like talk with people and, like help elderly people go shopping and things like that. And that really excited me. And there's a lot of, there are a lot of interesting questions. You have to think about how people think, and you have to, when you're building a robot, you're almost like building like a mind, right? So there's a lot of really interesting problems there. So I'm going to talk on a pretty high level about some of the core problems in social robotics, and also go into some details in some of my specific work, so you can sort of see the guts of how a few of these things work. So if I can, is my screen still being shared?
Yes.
Okay, totally not at the beginning of the presentation. All right, how is this? All right. So I'd like to talk about creating social robots, and especially the sort of trade-off between machine learning and manual design. Because there are a lot of questions about how we should really build these robots. And all the robots you see here are robots I've worked with at ATR, different versions of RoboV, and the one on the right is Erica, a very human-like android. So when I'm talking about social robots, a lot of the work that we've done has been in real-world locations. So we have like these robots that act as social peers. They act sort of like a person. They talk with you in conversation, with speech and gesture. And they're not like devices. You don't like give the robot a command and say, robot, do this, and then it does it. Instead, it like talks with you, and it hangs out with you, it plays with children. And real environments are really difficult. So shopping malls, there's so much noise and music playing and things. Train stations are very noisy and chaotic. So there are a lot of challenges of sensing. There are a lot of challenges of actuation. So it's been a really fun set of research work. And so what I want to talk about is how we're going to program social robots. And I'm going to touch on a few different issues like scalability, robustness, proactivity, character, and intentionality. And what I mean by these things, scalability, how many actions can the robot perform? How many speech actions or moving around or picking things up? Is it on the order of 100 or a million? That really matters, right? If it has, what level of human-like interactivity can it have? And so who has to create these behaviors, whether they're programmed or learned or whatever? Is it many people? Do you have just one really talented author? Do you crowdsource from the web? Do you allow non-technical people to input stuff to the robot, or do you just need programmers for it? There's ideas about big data or small, really clean data, right? And machine learning. So all of these things relate to the scalability of the robot's capabilities, right? Robustness, if you just think of social interaction, different people have different interaction styles, different ways of talking, different needs, different things they can do. So you really have to learn how to do a lot of react to a lot of different stimuli and interact with people in different ways. And proactivity is a particular thing that I'm interested in because, with all these personal assistant, smart speakers and things, a lot of these very passively answer questions or commands, right? And they're great at doing it, and they've solved a lot of really hard problems, but they don't take action. They're not a part of your life where they say, hey, let's do this now, right? And so if you have a robot and you want it to take action, what should it do? That's actually a really hard question because it depends on what is the purpose of the robot and the background of the robot and the character of the robot and the nature of the social situation. So it's really hard to think, how would you even program that, right? So proactivity is a big one. Character. And the graphic on the right here is it's based on Westworld. If you guys you've seen it, you're a robotics club. And I was really inspired by that, the ability to parametrically control each aspect of the robot's personality, right? That's huge if you want scalable stuff. Like if you program a robot and you spend years doing it, and then you want a robot with a different personality, how much extra work is it to tweak that, right? Or do you have to manually craft every character? So that's a question that I'm going to come back to a couple times. And then intentionality. So, you can program a robot to do anything, right? But are its behaviors actually structured and purposeful? And, are they legible? Is the character consistent? This is very important, if you want to know what to expect from a robot. And, I keep coming back to the, Asimov's 3 laws of robotics, which I'm sure you guys know, but that was, a vision back, decades ago of, robots figure out how to do things all on their own, but they have to adhere to these laws. They can't hurt human beings. They have to follow orders, things like that. And most robots and most autonomous systems I see in the world aren't really structured in this way. So I've really been thinking about how can we move in that direction so that, no matter how the robot's programmed or designed, it follows some sort of consistent set of behaviors, which I think is very important in structuring the robot's mind. So I'd like to talk about, this is just my categorization, but I see 3 different approaches to, planning a robot control, whatever you want to call it. And I don't have a good word for this first one, but, first principles, I'm thinking things like cognitive systems and symbolic reasoning. So, like Sherdlu, maybe some of you have heard of it, but classical AI, a lot of rule-based expert systems and things, you say, pick up the big red block next to the green cone, and then, the system will analyze everything that you said and figure out what it means and tie it in with an ontology or some semantic models and figure out what to do and take action, right? And I think that's how most of us expect robots to work, right? They dissect everything, they're very logical in their reasoning, right? But in practicality, it's building up a logical, consistent cognitive system that can handle all of the noise and the chaos of the real world and all the ambiguity and things. It's a really, really hard problem. So I think those systems don't really, well, they're not really that practical at this time. But that's definitely the goal that we want to get to, I think. Another one is manual programming, and I'm showing some pictures of flowcharts here because that's how I've built a system to program our robots. And that's where you say, okay, first the robot should do this. Then, depending on what happens, it should do, A or B, C or D, right? And a lot of this is sort of scripted. So if you want to have creative people like authors create, a story for the robot to tell, or a way, if you have a therapy robot and it has to ask people questions in a gentle way, you want somebody to be able to script that and control that at a very fine level of style. And that's not really easy to do with a first principles system, in these cognitive architectures. But it takes a lot of work, to do this by hand. So this other direction, data-driven stuff is what I'm very excited about the last few years, and I'll show a lot of examples of that. And basically, this is imitation. If we can watch people and see what they really do and learn from that with neural networks or other techniques and reproduce it, it's sort of content versus form, right? And this is like reproducing the surface behavior of what we do. And you can actually go a long way, because if you think about it, that's a big part of how children learn, right? They imitate what their parents do. They imitate what their friends do. So I think it's going to be a very important cornerstone to these different approaches to how robots will think and plan. And I think all 3 of these are very important, and I'm going to look a bit at the connections between them. And the second sort of big concept that I think is important to keep in mind is this idea of sense, plan, act. Some of you may have heard of this. It's just sort of, this is what robots do, right? They sense the world, they plan what to do, and then they take action. And there are different approaches like, subsumption architecture, or things where act and sense are closely connected. But basically, these are the three components, however you connect them. And I'd like to break it down a little more. And sensing is partly about collecting raw data about the world, and partly it's about understanding, creating semantic models, or making sense out of the world, not just sort of having lots of input. And then action, you can also break up. There's abstract actions, which is like what you plan to do, like I want to pick up that block, or I want to, convince this person to buy a camera. But then there's concrete actions, like how do you actually do that? How do you actually talk to this person? How do you inflect the voice, or what kind of gestures do you make? How do you position your body, right? How do you grasp a block? And then, of course, in the middle, I talked about different approaches to planning. So I just wanted to share those as like an overall framework of the core concepts here, and then I can go into a few of the research projects I've done that touch on these issues. So one is about modeling human behavior. It's about that perception side of semantic understanding. And this is a study we did at Universal City Walk in Osaka. So it's the shopping mall outside of Universal Studios. And we deployed robots there for like a year and a half. And we had them driving around and sort of talking to people and giving directions and recommending shops. And so there were a lot of challenges with deploying robots in a real space like that. So first we have to understand the environment. And these are pictures of the place where we ran the robots. And like where do you even start, right? Like understanding what do these spaces mean? How do you use them? So yeah, this is what it looks like with a robot. You might not be able to hear me over the noise of the video. But basically, the robot is slow, people are fast, the robots have to navigate through the space, and we have to understand where people are. So we set up these laser rangefinders. They're much smaller these days. This is a very old model from about 10 years ago. And we placed them on poles around the space so we could just study how people move. And we used the rangefinders to track people. And then we did some interesting investigation to the pedestrian motion and patterns. So for this study, we collected over 10,000 trajectories over a week of just how people walk at different times and places. And I won't go too into the details here, but we classified aspects of quickly walking, slowly walking based on speed, angle, velocity. And we created a real-time system that can interpret people's motion as it's tracking them through the space. So you can see all the people here being tracked by the system. And what it's doing is tagging them according to their actions. So are they running, are they walking quickly, walking slowly? Are they changing direction frequently? So this particular guy is he's walking straight, he's busy walking, he's running, he's carrying some stuff and going quickly. And we can monitor, the whole space and identify, these macro level actions that people do. And so we can figure out if they're window shopping, if they're in a hurry, things like that. So we did a few studies where we made like a spatio-temporal grid so we can map out how space is typically used at different times of the day, different days of the week. And so you can see I don't know if you can see my mouse cursor here, but this pink area in front of the shop, that's where people are sort of window shopping and walking back and forth very slowly. And then at different times of day, like during weekdays in the middle of the day, people just walk by quickly and nobody's shopping. So you can kind of understand the purpose of some parts of the space. Like these black areas are where people stop for a long time. And those are rest spaces and benches, right? So we're starting to understand the semantic meaning of the space, not just tracking raw data of where a person's location is. Now, the really cool thing that we did, I think, is we look at people's trajectories and we kind of cluster them together in an unsupervised learning way. So we're not ascribing names or meaning to this. We're just saying these are similar to each other. This is a typical pattern, right? And what we're able to do is figure out these clusters of specific trajectories through the space, from a certain area with a certain primitive moving in an area. And then you can cluster those as an entire trajectory across the entire space. So the reason we do this, the cool thing is that as somebody comes in, you can match them to the known trajectories, and you can build a probability map of where they're going, right? So basically, we can tell you where a person's going to be 15 seconds from now and what they're going to be doing. So we're kind of reading the future. We're anticipating human behavior, and that's really important for robots because if they move slowly or they have a lot of difficulty sensing. So they want to know where the person in the red is going to be in these green areas in 5 seconds or something. So the robot can pre-position itself or anticipate what the person's going to do. So here's an example. The robot's this blue triangle, and you can see some people approach, and it's projecting where they're going to be, and it's going to pre-position itself to approach them. And approaching people is a big problem that a lot of people are interested in robotics because there are a lot of little social signals and anticipation that goes on, and it's quite difficult to do, and sometimes people walk right by. But we were able to successfully do that in this space. So that's an example of that sort of sensing and semantic understanding, right? Now I'm going to totally jump topics to Erica, and she's our android that I worked with for about 3 years, and I was the lead architect of her system. So I built basically all of her top-level control software. And so Erica looks like this, and she's got 19 degrees of freedom. The black actuators in the diagram are the ones that have that are actuated at the time. Actually, now her arms work, which is really cool, but I don't get to use them. She's fully self-contained, which is great. All of her actuators are like inside of her torso and stuff. So you basically just plug in power and network and like a pneumatic pressure tube, and that's all you need. So some of the older robots have like these big boxes with like valves and stuff, and she's like very portable, which is great because we were able to take her to a lot of locations. She's very realistic. She has cameras in her eyes, microphones in her ears, and stuff. But usually we would set up like an environmental sensor system to track people and support her her cognition and her interaction. So one of the cool things that she has is expressive speech. So not just regular speech synthesis, but we can add in these markup tags that give emotion and laughter and interest and surprise, which is just like really, really cool. It adds a lot of lifelikeness to the robot, and this is what I mean by concrete actions, like really making the robot express something in a certain way in its voice is a very important part of not just planning what it should say, but doing it in the right way. So there's some sounds here you can hear. This is like with no emotion. Oh no, the timer's on. And then here's with the emotion tags in. Oh no, this is totally messed up. Let me stop this and not use the timer. I don't know how to use a Mac. This is a new thing for me. Okay.
It's okay. It's intermission time then.
Sure. All right, let's just try this again. All right. So here's just another example. 信じられない。そんなこと言うのひどすぎます。And then an embarrassed one. 本当に？素晴らしいですね。なんて言いますか。そんなことないと思いますけど。本当に？ Anyway, you get it. Oh, jeez. Right. PowerPoint technology. Anyway, you get the point, which is that she has this like very, very expressive voice, and you know she doesn't have that many actuators in her face compared with, for example, some of the robots by like Hanson Robotics. You know, they have these like incredibly realistic facial expressions. But my feeling is that the expressivity of the voice actually really brings the interactions to life in a very effective way. So the way we control her, I don't want to go too much into the technical details, but we control most of our actions through this sort of flowchart interface. And each block represents a programmatic backend module. So, you know, things like shaking hands or talking or driving. We use the same thing for RoboVN for Erica. And this is the manual programming stuff I was talking about. So people build these sequences of interaction. You know, this is basically programming, but it's in a visual way so we can get non-technical people to do it. And you get all sorts of interesting patterns and really complex stuff. And we get thousands upon thousands of these behaviors being programmed into the system to the point where it's kind of hard to grasp all of the capabilities of the robot because so many people have kind of contributed in different ways and built these different modules and topics you can talk about. It gets a little difficult to manage once you get to a certain level of the scale, but I find it's pretty effective for at least this research level stuff and the demos. And here are some examples of what you can do with the manual programming that would be essentially impossible with you know, first principles systems and typical approaches.
こんにちは。
実は仕事とは全然関係ない話なんですけど、ちょっと気になっていることが。
どうしたんですか？はい。
私、普段はここで研究所の人たちとお話ししてるんだけど、最近会える人がすごくよく会いに来てくれるの。
はいはい。
それでね、私のことを好きって言ってくれるんだけど、私、まだそういう気持ちがあんまりわからなくて、
なるほど。
あなたは好きな人とかいるの？
は
ないの？
はい、います。
そうなんだ。
はい。
やっぱりみんな好きな人もいるんだね。
まあ、みんなではないと
そ
思うけど、
の人はあなたのことが好きなの？
すごい好きだと思います。
Anyway, we don't have to watch the whole thing, but you know, the thing here is that you know, we actually put this robot out in like a bar and had her like talking with people, and you know, the idea is like to get, you know, to engage people in like an emotional level and show the robot's intention and stuff. And you know, there's so much work that went into, you know, the underlying aspects of this, like the little gaze movements and the head movements and the emotional expressions and the pauses. Some of that was automated and according to models, and others were sort of scripted, but you know, it's a great way to explore, like, how do we actually have a real interaction with a person? There are a lot of challenges to manual design like this, so you know, it's hard to anticipate what people will really say, right? Because social interaction is so open-ended, and it's hard to articulate, you know, what people would naturally do. Like, it's easy for us to interact socially, but it's hard for us to explain what we're doing and why we're doing it. So hand coding stuff like runs into a lot of limitations that way. And so that's why I really got into this idea of learning behavior directly from humans. So here, this is RoboV again, and we did a lot of studies in this sort of camera shop scenario, learning data, like learning interaction logic directly from data. So the idea is to observe human-human interactions, record what's going on, and then reproduce the role of one of the people with a robot, and see how far we can get with that. So we set up this sort of fake camera shop in our lab. It looks like a typical lab study environment, but we put some sensors on the ceiling to track people. We have some cameras around, and the robot would drive around and answer people's questions about the cameras. You know, how much does this cost? What kind of optical zoom does it have? Things like that. So we recorded a bunch of people with the sensor network and with these little Android phones. And there were a number of research challenges representing this high-dimensional action space, dealing with the variation of social behaviors between people, and a lot of sensor noise. Like, most of the speech recognition had errors in it, which is not really the case if you're talking straight into your phone, but it's true in the real world. Basically, what we did is we took what people did and we extracted abstracted representations of them. So, you know, things the shopkeeper did, things the customer did, spatial, speech motions, and also the proxemic spatial formations of them. We took a time sequence of them, and we trained a machine learning predictor with that. So there are a lot of unsupervised learning problems, sort of like what I just presented. So we want to figure out where people stop in the room, what are the trajectories that they use when they walk, and what are their typical speech utterances. So we did this with clustering very similar to what we did in the shopping mall, and we found the trajectories and the stopping locations. We did a lot of speech processing. I won't get too much into the details. And we used existing proxemics models that have been investigated in other robotics research. So, like, you know, there are some models that explain how do you present an object to somebody, how do you approach somebody to initiate a conversation. And we incorporated those into our abstraction model. So we have things like waiting and face-to-face and presenting a product. And we clustered the speech as well. So this is in a very, very high dimensional space we're clustering it. But, you know, people would say this is $500 or something like that. You know, this costs $500. How may I help you? How can I help you today? And it would cluster these speech things together with the same semantic meaning. And then we did the tracking clustering and, you know, the proxemics models, and we put these all together into a classifier that's able to predict these pairs of one customer action leads to a shopkeeper action. And these are recorded from these example interactions, and the robot was able to reproduce them. So yeah, let me skip this. And these are just the information that goes into the joint state vector that is used to predict the robot action. So here's an example of an interaction that our system produced.
Hi, Sarah. Let me see if I can help you with today.
Yes, this camera. How's the battery life?
Long battery life of 9 hours.
Oh, I see. And the weight?
This camera is 115 grams and the can fit in your pocket.
Oh, wow, that's very convenient. Thank you.
Okay.
How about this one? How's the storage memory?
Yes, I'm stored 10,000
How much is it?
This is $400.
What colors does it come in?
The intense rain red and brown colors.
Oh, actually. What's the optimal zoom on this camera?
Optical zoom.
Okay, thank you.
No problem.
So in there you can see a few examples. You know, it's reacting to her location in the room, not just what she's saying. She says, how much is this one? It knows where she is. Then sometimes there are errors in the speech, or, you know, things are phrased differently, and it's able to handle that noise pretty robustly. But on the other hand, there are also some noise in its, so it said like intense red, gray, and brown colors, but I think the original thing it learned from said it has, but that was a speech recognition error. Anyway, this is a really cool approach, I think, and we spent a few years investigating versions of this. So the cool thing is that it's completely data-driven, and there's no human designer, and it requires no semantic understanding. So the robot didn't understand what it's saying. It just knows that those words are appropriate in that context, right? And you get sort of an interesting lifelike variation. So we explored a few more things about this. In particular, we're looking at learning personality. So again, you know, that Westworld thing where you have the slider. I wanted to see, you know, how much we can achieve that. So we got two different shopkeepers to come in. One guy was very proactive, loved cameras, very talkative, and he would just talk about this stuff so much. And then the other one, she was very polite and very sort of quiet, and she would just kind of answer questions if you asked her, but she wouldn't really volunteer much information. So, you know, we set those two as endpoints, and you can see like a slider here. The idea is that if we can train with a deep neural network, and we have the proactivity level as an input parameter, then when we run it with the robot, we can tweak that value to whatever we want and output that personality with the robot. So it gets a little technical, and I don't really want to get into too many details, but we used a deep neural network with what's called an attention mechanism. So these green things here are like the input vectors of like t-1, t-2, t-3. It's like the history of the interaction. And then these this other network learns attention values. So it puts weights on the different things. So given a certain utterance, actually it's really important what they said previously, not what they're saying now, and things like that. So it gets a little complicated. We have papers on it that you can read if you want. But the cool thing about neural networks is that you can make really cool plots. So the plot on the left here is the neural network before training and then after. So if you see like the light blue and the dark blue, or the light red and the dark red, you know, the light is the passive shopkeeper and the dark is the proactive shopkeeper. And what this is the last layer of the neural network, which is a very high dimensional space, and we condense it down to two dimensions. So what you can see here is like the red is like kind of far apart. Like all of the stuff from the one shopkeeper, all the stuff from the other shopkeeper are clustered together, but they're not near each other. But after the learning, it actually learns that these go together, these go together. It finds similarities in the behaviors of the two shopkeepers, which is really kind of neat to see. And each color is a different camera. So there's like Nikon, and this is Sony and Canon. So it was just interesting to see that like it's learning these representations that kind of map to our intuitive understanding of you know, the semantic meaning. And if you zoom in, you can see like the circles and triangles are quite near each other. So yeah, I don't have to go into the details here. But they said similar things, but in different ways. So like one might say, oh, it's got an APS-C sensor. And the other one says, oh, this has, you know, 3 lines of text. So it's just interesting to see how the learning works, right? And like it's learning all the different features of questions for each camera together. And I'll kind of skip around in this video, but this is, first here's some of the data we learned from. And you'll see the difference between the passive and the proactive shopkeeper are often important when the customer does nothing, when they're silent, right?
Excuse me. How much is this camera?
So this is the passive
That one
shopkeeper.
is $550. Is this easy to use? It has preset mode, so it's easy to use. But if you want to adjust the settings manually, you can also do that. I see.
Also, the passive shopkeeper didn't jump in when she had a chance to maybe introduce new features.
What are the colors you have? That one comes in white, silver, and black.
Okay, so that's the passive shopkeeper.
That's pretty good in low
Here's the
light
proactive
conditions
one.
up to MIDI. Please pick it up and take a few pictures. Okay. The general rule is the heavier the camera, the better the camera. At 500 grams, this is an excellent quality camera.
So you can see the shopkeeper taking initiative here.
It's designed for travel, so it's all about taking great pictures in a lightweight package that doesn't get in the way.
All right, so let's skip ahead to some robot stuff. Here's the passive robot.
Hi, I have a question about this camera.
Sure.
How much is this one?
Just the body of only it costs $2,000.
Okay. What about the sensor size?
It's a full frame runner. If you need anything else, I'll be at the service counter.
So, passive robot.
It's our next camera.
Okay.
Proactive.
How much is this?
The camera body is $2,000 and rings our next camera.
Okay.
Here is our business card and the brochure. Come in and set you up and you can use it test chart.
What about the sensor size?
This is a full frame CMOS sensor, which is part of the reason it takes such good pictures in low light. Full frame is the same size as a piece of 35mm film, and that's the standard for a top-end camera.
So anyway, you can see we were able to some extent to reproduce the personality of that shopkeeper, and it's a little hard to show in a video, but you can move the slider in between and go 50-50 or 20% proactive, things like that. So this data-driven approach is highly scalable if we can collect big data. So if we could passively collect this, say, in department stores across the country or something, and then for a couple of months, collect thousands upon thousands of interactions, we could get some pretty interesting behavior from the robot, I think. It's pretty robust in the sense that you can phrase things in many different ways and it can react, but it's also fragile in other ways. It really depends on what kind of data you collected in the first place, and is what you're doing similar to that data. It's proactive in the sense that it can reproduce proactive behavior that has been demonstrated, but it doesn't come up with its own new behavior to proactively do. And then with character, like I said, we're able to kind of interpolate between some learned models. And intentionality is a hard thing to talk about, but it's not really intentional. Sometimes it seems that way, but sometimes the behavior seems kind of random or inconsistent, maybe because it's just not understanding enough or modeling enough things in the history. So there's some pros and cons to that approach. And the last little topic I want to talk about is this thing I call intention-based planning, which is kind of trying to bring together several of these principles, but using a first principles approach to launch them. So like I said, generative language, cognition, and things are very, very hard problems. And it's very difficult to automate things like style or character. Dealing with noisy sensor data and ambiguity of meaning is also hard if you're making hard-coded rules, for example. And yeah, there's a lot of challenges there. And so manual authoring is a lot better in many ways, but it lacks structure and explicit meaning, right? You can write a script, but there's nothing that guarantees that that script is consistent with a set of principles or anything like that. So I came up with this idea called intention-based planning. And if you think about navigation robots, they often separate high-level and low-level control. So on the high level, they'll do global planning, maybe with like a map of a space. Say, I'm going to move to these waypoints. But then as it's driving, it does local planning, because maybe there's junk on the floor and it's avoiding obstacles and things like that. So what I'm proposing is that for conversational interactions also, a designer can specify a set of high-level intentions for the robot. And then the robot can choose actions based on those intentions. And then the low-level interaction control is handled with the scripted interaction content that is associated with those actions. So to do this, we need a state model, which has like the conversation history, the user state, and then a set of actions that, things the robot can do, right? And these affect that state model, and they change it. And then we have a bunch of intentions, which are basically, what do we want the state model to look like? What do we want the world to be? And those are utility functions that have different value, right? So some example actions that we made for this demo are like greeting a person, asking questions about the person, where are they from, what are their opinions about robots, things like that. Maybe presenting some information about the robot. So this was for Erica, and we often have visitors for Erica, and people want to know about the robot. So we built a bunch of behaviors for that. Then, answering questions if they ask specific questions, and then saying goodbye, right? So that's a very simple set of actions. And for each one, we built these flowcharts, right? And then intentions. We made the robot want to greet new people when they arrive. We want to answer questions if they're asked, initiate new topics when there's an opportunity to do so, avoid repeating itself, right? So these are not concrete actions. These are principles. These are intentions for the robot. And then again, this parametric control of character is something I'm really excited about. So we made an intention where she can try to get a certain ratio between learning about the person versus talking about herself. And you can set that. So if you crank this all the way to talk about herself, then she's very egocentric and full of herself and just like, oh, I'm the best robot ever. And you crank it to 0 and she's just interested in other people. So I feel like that's another example of how you can, parametrically adjust a personality, even if you've already built the content. So the way this works is you take a current state, you imagine, like, if I were to do action 1, how does it change the world state? If I do action 2, how does it update the world state? And so we create this set of imagined states that we can evaluate. So you can evaluate on a grid. If I take action 1, it changes the state in some way, and then all of these intentions are evaluated, and we see when the utility changes. And so we can figure out, okay, which actions give us the best utility increase, and so we can select those actions, right? So that's kind of how a lot of general robot planning systems work. And yeah, a big diagram of how it works. So this is kind of a long video, so I'll skip around a bit. One of the things we also programmed her to do is to follow a sequence of conversational phases. So after greeting somebody, then she can introduce herself, things like that. So I'll pause this right here. So here you can see these are all the intentions we turned on. We can turn on and off the intentions. And then she's got a conversation phase and stuff. So here a person approaches. And it detected somebody arrived, and it wants to go to a greeting phase now in the conversation. And once it's there, it really wants to greet newcomers who have arrived. So it selects the action to greet them.
How is it going? It's going great. It's going great. Good to hear. My name is Erica. I'm 23 and I'm one of the most advanced android in the world. Oh.
So here, she just said, cool. So she didn't take any initiative, right? So now the robot has a chance to do something. And since it has this intention that says it should initiate new topics, it picks a random topic and talks about it. Based on how it's going to...
The rainy season just finished. The weather has remained hot and humid. My colleagues said that getting up and preparing to go to...
All right, so here there's an interruption. A second person arrives.
Hello. I didn't know that you were coming in today.
And now it goes back to what it was doing before, because the interruption's finished.
Pardon me. The rainy season just finished, but the weather has remained hot and humid. My colleagues said that getting up and preparing...
Anyway, we don't have to go through this whole one, but the idea is, what I wanted to show is that even though the utterances and things that she does are scripted at some level, we have this level of intentionality and and like a higher level that's actually dynamically choosing what she should do. So she's, in some sense, she's thinking about what she's doing. She's not just following a script mindlessly. So anyway, this sort of thing enables the robot to handle interruptions. We can choose its proactive behaviors according to a set of principles, how it's going to affect the world state, rather than just sort of hard coding things. And then parametric control of the personality and scalability, because now you can easily add in a new sequence, like an utterance, like a little flow chart, and say, this is how it changes the world, and the intentions will figure out what to pick. They don't need to know what actions exist. So just to summarize, these things I talked about, these first principles systems, cognition, reasoning, I think this is what most people expect of robots, and I'm hoping we're going to get to the point where robots do think this way. We certainly will, and people are working in those directions with consistency, but they're highly complex. So we've got manual programming, which is much more controllable, but it's hard to design well for a number of reasons, and there's no intrinsic structure to it. And then there's data-driven learning, which is, can be very robust to certain kinds of inputs, but it's also kind of hard to control. And the only way to control it is to train it with new data, right? You can't tweak it or debug it the way that you can with manual programming. And it lacks some sort of intrinsic structure. So like if you change the price of the camera, that kind of messes up the whole system, right? So you need more layers of understanding and semantic modeling to make this ready for the real world. And then this intention-based planning thing is just one possible way that we can link these ideas together into a consistent, coherent system. And finally, I made this, my lab made this video that illustrates a few of the things. So I'd like to show this. I hope it's not too loud for you.
The hippie to the hip hop, and you don't stop. A rocket to the bang bang beat, say up jump to the beat, to the rhythm of the beat. I am Robotics, and I'd like to say it aloud. I got the plastic and the steel, the gears and the wheels and the motors that make me go. But first, I gotta talk about some research that's critical. I'll announce it to the nation. My social interaction logics obtained through learning by imitation. Check it out. We got some humans to perform example interactions. And when they move and when they spoke, we discretize their actions. Keep it rocking, you don't stop. For our scenario, we use the camera shot. We use unsupervised clustering and trajectory segmentation to identify action primitives from clustered observations. And with this data, we went ahead and trained a classifier to generate robot actions from the data we acquired. Either utterance, trajectory, and proxemic formations through the data-driven process with no human annotations. And now I have learned to move to places in the room and talk about counter aspects like shutter speed and optical zoom. Bang bang, the boogie to the boogie, say up jump the boogie to the robot boogie, let's rock. You don't stop, rock the rhythm that'll make your robot rock. Now so far you've heard my voice, but I brought a friend along. And the next on the mic is Erica. Come on and sing that song.
Check it out, I'm the E to the R, the I C the A, and I'm built for HRI.
Say what?
My silicon brings all the bots to the earth, and these reasons I'll tell you why.
Check it out.
I'm the state of the art, the top of the line, and I'm rapping to the rhythm. Yo, Robo, I can learn too, with a similar algorithm. In a travel agent scenario, we collected utterance data, but it turns out that with speech alone, the challenge was much greater. You see, it's much more difficult to make predictions if you don't have spatial cues. But with a new algorithm for modeling topic, I don't have to be confused. The elegant thing is, I have no need to understand what's being said. I use metrics of co-occurrence frequency instead. With clustering, we managed to make an approximation of the current topic without using semantic information. And now I can generate behaviors on the fly.
That's right.
Learning from example, data-driven HRI. If you're having robot problems, I feel bad for you, son.
I got 99 problems. But learning by imitation from human-to-human interactions ain't one.
That was just sort of a fun video we made to illustrate some of our research. I didn't go into the details of that second thing with the topic detection, but it was another exploration of how to learn from data. So that's kind of what I prepared for today, but I'm absolutely happy to take any questions that you guys have. And I hope you found this interesting.
We did. Thank you very much. And now, first, I know we're going to do the questions, but I submitted you there were some pre-questions. And if you got them, if you can deal with those first, and then we can do the ones that are in here.
Okay, sure. Yeah, hold on. I have them on my phone here.
A lot of unique questions.
Ones. So yeah, one of the questions, let's see. Okay, the last one you sent me said, hold on. Yeah, there were a lot of very interesting questions there. Where is this list? Well, one of them I remember was about Go. I guess somebody knew that I like to play Go. And they were asking about my reaction when I found out that AlphaGo had beaten the world champion. So I absolutely love Go. It's my favorite game. I recommend all of you guys should learn how to play. It's very simple rules and really interesting strategy. And the thing that really got me the most about that, the fact that a computer beat the Go champion, because that was always one of the, people said, oh, computers can beat people at chess, but not Go, right? Because it's computationally complex. But really the interesting thing to me was that if you think about it, like some people look at it as, oh, thank you. Some people look at it as like humans against robots, right? And like the robots are beating us and we can't keep up, right? And that's a very a confrontational kind of perspective that a lot of people have. And you can keep that in mind, but I like to think of it as a collaboration. So if you think about it, like if you're learning how to play Go, you go to a Go school and there are people who are better than you, you learn from them, right? And actually the Go community in the world has been on fire now, right? They're like learning all these crazy new moves and crazy new strategies that are, these computers are coming up with. And it's improving the way humans play, right? It's helping us become better players because we're learning, we're seeing these better things, and that helps us grow in different ways, right? So I think that's going to be one of the most interesting things that AI is going to contribute, is that it's going to make us more intelligent through our interactions with it and through studying with it. And I read like an interview with, they hired a Go professional, like a professional player, to help train the system. And he got substantially better at Go through the experience of training AlphaGo. Because it just kept coming up with these like new reactions that he hadn't anticipated, and made him think in different ways. So I think that's a really positive thing, and I think it's a really exciting thing for humanity in general. So let's see. First question here was, as AI technology advances, many believe robots will achieve human-level consciousness. In the context of reflexivity, what is the current capacity of these social robots to recognize forces of socialization and alter their own behavior? Whew, that's great. So yeah, I guess if you just watched my presentation, then you're probably thinking, oh, these are pretty dumb robots. You just like program to do some script and then they do a thing. And hopefully you saw that there's a little more below that. There's some underpinnings, there's some structure, and especially with the learning, they're starting to do things that we can't even anticipate. But we're a long way from, I guess, what we would consider human consciousness. But there's a lot of research going on into robot cognition and human cognition. I think there's some other questions that touched on this as well. So what I think is going to happen is that as we understand more about how reasoning works and how emotion works and how understanding itself works, we're going to build little test systems that reproduce aspects of this. And some of those, once we know how it works, we can scale things up with computers that we can't do with people, right? So we're going to have computers that are much better than people at very small tasks, I think, first. And I'm not even sure what reflexivity is. I assume it has to do with like, self-awareness or something like that. I think self-awareness on some level is actually not that complex of a thing, and it's going to be very necessary for robots that, especially robots that engage in lifelong learning, which is a very hot topic of research. So, as you have a robot, that learns how to walk, and later its environment changes or its body changes, or it starts wearing down, it has to relearn things. It has to dynamically, it has to know which information to keep and which information to discard over time. And people are coming up with ways to do that using deep neural networks and things like that. So, in some sense, there's implicit self-consciousness there on some level. But I don't think we're, we've got at least 30 years before we have to really worry about anything. Is my perspective on that. Let's see. How soon do you think our humanoid robots will reach the dexterity and level of cognition of robots depicted in the movie I, Robot? So basically human level. So dexterity is definitely going to come first. And, if you've seen Boston Dynamics stuff, that's just incredible, right? And, doing things like jumping or climbing is... So I think one of the things that makes that... I would never say that's easy, because I know it's really hard stuff, and I've studied some of that, and it's really hard. But in some ways, those physical feats are much easier than things like social interaction. And one of the reasons for that is that you can do simulation of it. Right? And I think there's some other questions that touch on this. But the idea is, if you can simulate what it's like to climb a wall, and then you can just run a system to simulate it, 100 million times, and learn from its mistakes in that, you can make a lot of progress towards learning a task. But simulating users, simulating people, if you want to try to convince somebody to buy a camera, like how do you even simulate like the realistic kind of users that you would be interacting with? And so that gets to the next question 4, which is what simulation environments are best for experimenting with humanoid robots? So I think there are a lot of good physics simulations and things out there. So if you're talking about humanoid robots in the sense of bipedal locomotion, or like these latest DARPA challenges with the robot has to be able to open a door with a doorknob and like pick objects up, definitely simulation is huge there. You can never really simulate everything, so you got to do tests in the physical world. But I would say that with social robots, it's much more difficult to simulate realistic human behavior. You really have to interact with people, and that makes it much more costly to collect human-robot data, because you don't want a robot that's going to fail in its interactions, interacting with real customers, right? If you have a brand, you don't want to put robots out there that are like telling them wrong information about the thing you're selling, right? So how do you practice? It's really hard to practice being a person, right? And I think we forgive little children for making mistakes because they're little kids, right? But like a robot that doesn't look like a little kid is not going to, so like we really do learn throughout our lives, and that's a big open problem. And that's one of the reasons that I focused on learning from human-human interaction. Because if you can passively collect what people really do, if you can observe them from afar, you can actually sort of imitate them, which kind of sidesteps this difficult problem. Let's see. Given that awareness and consciousness seem to be a matter of brain size and complexity, looking at amoeba to human, do you foresee any reason that our humanoid robots will not truly be conscious one day, rather than zombies with only the appearance of consciousness? So yeah, that's that's philosophical. So that's one of those things that people have debated for centuries, actually. And how do you even know if someone is or something is truly conscious? And if it acts conscious on the outside, how do you tell if it's really conscious on the inside? And I think the answer is you can't. But the further answer could be, and this is of course debatable, but that it doesn't matter. And sort of the fake it till you make it approach. If it acts in all those ways that it appears conscious, isn't it basically conscious, or isn't it good enough, right? So you can argue different ways about that, and one of the arguments, I think, people talk about what are the risks of, especially Erica's this like beautiful woman robot. So people talk a lot about like, oh, would people fall in love with robots or something like that? And one of the, people are like really making, companionship and like sex robots and things in the real world. Like it's a real thing now. It's not speculation. It's not science fiction. So people are talking, okay, what are the actual problems of this, right? And one of the problems is that it's the emotional connection is one way, right? Like the robot may act as if it is emotionally drawn to you, but if it's not really constrained in the way that we are, then it's an asymmetric interaction, and that can cause some problems, psychologically and things like that. Especially if the robot does inconsistent behavior, right? So if it acts like it's totally in love with you one day, and then the next day it's like, doesn't like you. If a person did that, that would be like devastating, right? And people don't typically do that because typically they're driven by their underlying emotions that they don't have control over. But if robots don't have a consistent model like that driving them, then they are likely to be inconsistent. And that is why I was talking about this intention-driven architecture and this idea that the action selection has to be driven by some sort of underlying principle. And whether those are designed or not, I think is not the point. The point is that the robot's behavior has to be consistent in order for us to trust it, in order for us to interact with it in a real way and to believably invite it into our social space. So I don't know if I answered the zombies question exactly, but I think it touches on it. So have major brain research, things like Human Brain Project and the Brain Initiative, revealed and released any findings that are critical to the direction and progression of the research? So yeah, that's interesting. My lab in both in Osaka University and ATR, a large chunk of our lab is actually working on BMI, brain-machine interfaces, and brain-related research. And there are a few different reasons for that. One is that we want to try to understand how the human brain works so that we can mimic it and create something that's similar and can perform cognition, right? And of course, nobody's really cracked the whole brain, and that's like a huge, huge open problem. And people have made a lot of really interesting progress, and a lot of the deep learning has become so hot in the last few years, and a lot of these structures that people have been creating for learning have been inspired by the human brain. But the fact is they don't actually work the same way the human brain does. So I haven't done any of my work in a direct way inspired by the findings on like real brain science, right? But see, the other side of it is that a lot of people are interested in like, one of the hard problems of social robotics is sensing and perception and like understanding social situations, right? Like people give off all sorts of subtle cues, when they're speaking, their body language, their timing, their overall, vibe and energy level. And those are like notoriously hard to capture, right? You see emotion recognizers that figure out if you're smiling or not, but still a very open area of like research. Like, how do we figure out what a person's thinking? What's going on inside their head? So if we can use things like, EEG or other, techniques to sort of extract, okay, this is what a person's thinking, maybe the robots can interact with us more effectively. And, we want robots to interact with us. We want robots to make our lives better. In order to do that, they have to understand us. And understanding is a really, really hard problem. So there's a lot of work that's pushing into, okay, can we use these new advances in brain science to increase our understanding of people's internal states? Yeah, so the next question. Google seems to be trying to generalize how to pick up variably shaped objects in a camera's field of view. Are you or any researchers you're aware of going to share pre-trained models that generalize dexterous and bipedal robot environment sensing and interaction? Or for the time being, will models necessarily be specific to each robot due to the relative infancy of research in this area? Okay, that's a packed. So one of the things you might have noticed from my videos is that we don't really use bipedal robots because that's so hard, and like if you can just not worry about that problem and put it on wheels, you can focus on the high-level problems. And that's what I was saying at the beginning of this. Seeing the robots that you guys are building in your lab, and it's really hard to build stable, robust, working hardware and make robots actually work, right? And so if you want to get to the point where you can talk about, consciousness, intention, emotion, like you need all those layers below it to be working. So I think it's the reason that we just usually use wheeled robots. So I haven't worked with these sort of advanced manipulation, locomotion things, which get in some very, very heavy math. And some people are doing really impressive work with that. And I think this question is referring to Google's like ARM farm, where they have like all these robot arms that are just trying to pick things up, and they've got, you know, hundreds, I don't know how many they have, and they're just over and over again, they're picking things up and, you know, observing what happens. And if you can gather enormous amounts of data with that, then you can start leveraging deep learning, right? Deep learning is really cool, but you need huge data sets for it to work. And of course, it's Google, so they can create those huge data sets. And so that's like a really, really interesting, you know, direction that robotics is working in. So part of the question here was, are we going to share pre-trained models that generalize? So the question about generalization, I think once you have enough layers, and if you've trained things in the right way, and if you have some really smart people controlling your system, you might be able to learn some generalizable things. And you know, that's definitely a hot area of research is you know, learn something on one system and adapt it to another system, right? Transfer learning, I think is the term for it. And so yeah, definitely that's a possible thing. But just because something is possible doesn't mean it's easy or practical yet. So, you know, wait a few years and I'm sure it will become much more widespread. But the other part of the question was about models, right? And I think, you know, it's not about the algorithms anymore, it's about the data. So, you know, if you have enormous amounts of data stored up, whether it's a corpus of speech for, you know, training your speech recognition, or a corpus of dialogue, or a corpus of picking up objects, or whatever it is, that is like more valuable than, you can just publish the algorithm you use, but if you don't share your data, you've got a lock on that IP, right? So if, you know, companies don't have much incentive to share their internal data, because that's their gold mine, right? So I suspect there's not going to be that much sharing of data outside of academic circles. I certainly hope there is. I hope there are a lot of open source, you know, grassroots movements to build up data sets, because then, you know, everybody can benefit from the data that everybody collects. But my guess is that that's probably not going to happen for a while. Someone was asking about synthetic muscles and progress I've seen happening in this area. I really don't know too much about actuators. I've played a little with shape memory alloys for a while. But yeah, I don't think I can answer that one. And yeah, how about biological energy sources for robots? That is, will robots one day consume food for energy, or will batteries and plugging in always be necessary? Yeah, I mean, energy is the big problem, right? Like, everything is limited by battery size and energy availability. And, you know, it's questionable whether food is really the best way to do that, because it takes a lot of water and energy and effort to raise food and harvest it. But I think, you know, this idea of energy is really, really critical to mobile robots. And a lot of the limitations, especially on flying robots, but even on, you know, driving robots, is like packing those batteries in. And that was like, you know, that was Tesla's big thing, was the batteries, right, in the car, which is really what made their cars possible in the first place. So I would say the only reason robots would actually eat food would be for social purposes. And if, you know, robots really need to blend in to human society, and if you get robots that can actually interact smoothly with people, and then you take them out to like a dinner meeting or something, and then the robot's like not eating, that would be socially awkward, right? And I think you see that in a lot of science fiction, you know, like fake eating for no reason. I bet that's going to happen. I actually suspect that's going to happen before actual consumption of food for real energy.
Annette, okay, so I think open up any questions in here. So those questions that he was answering, those were the pre-submitted ones. So that's why we need to do those first. But now we'll open up to the floor here. Now, again, these are questions. So if you're like just making a monologue, I'll probably stop you and tell you to get to your question, because I mean, we got to respect his time. So I'll open up the floor and I'll just repeat the question to Dylan. Question.
Tell me about the software. What languages do you write it in typically? C, C++, something else? Or I saw you had that diagram, that flowchart based software. Is that proprietary that you've written yourself, or is it off the shelf? Or
yeah, so right, for most of the stuff that I've worked on, often for like low-level driver stuff, we'll use C++. Just, you know, for the performance, and And then for higher level control stuff, I often use Java. I really like Java because it's much more friendly than C++ in terms of like I guess I've often worked with like large teams of people where people have different kinds of skill levels. And if you have a new student or an intern who comes on your project and then they mess something up and you just have like, a core dump, segmentation fault, that's just like, and it kills the robot. That's really painful. So I feel like Java is much better for like gentle debugging and, handling errors and things like that. So for anything that's not like really time critical and like close to the board, I often prefer to use Java. The flowchart, the sort of graphical thing that you saw, we did develop that in-house. I developed a prototype, and then we kind of farmed it out for like the better version of it. But there are a few other systems that use similar kinds of approaches. The idea of using visual programming is, for example, SoftBank that made Now and Pepper robots, and they have this thing called Choreograph, which is like it's kind of like My Software except much more beautiful and much more full featured. So you can actually go in and write Python code inside of it. So I really think that visual programming is a huge thing because when it comes to programming social stuff, you want people who are not just like coders to be able to have access to it. Because if you're relying on your best C++ programmer to go in and change like a the to an or something, that's just like really poor use of resources. So that's kind of my perspective on the computer language question.
Really interesting.
What's your question?
So, I saw that you're using a deep neural network, or you also showed us how you modeled proactivity using neural networks, I guess. So when neural networks work, it's nice, right? It's
what's the question? What's the question?
Oh, the question is, when the neural network works, it solves the problem. The neural network gives out a feature. But when it doesn't, let's say you have a couple of convolution layers and it doesn't classify your data, how do you go about tweaking, or how do you go about solving or getting the features which will do the classification?
Yeah, so neural networks, so deep neural networks are so exciting and such a hot topic, and like everybody's using them, right, and talking about them. But you're exactly right; they are like very finicky and difficult. And so actually, for a lot of the work we did, we've used other kinds of classifiers, other kinds of machine learning classifiers as well. But the most recent stuff has been neural networks, and a lot of this, what we've done is what our classifier is trying to do is select a most appropriate behavior. And so sometimes what you can do is you look at the top few most appropriate behaviors and select from those. But really, like in terms of real time, like during operation, there's no particular technique, whatever we're using. We're just kind of running it. And we get a pretty good hit rate, but it's not 100% perfect. So if you were to make a production system out of that, then you would definitely need a lot more work on that, on the neural network side. In terms of tuning and tweaking and building up the offline learning side before you're ready to run it, there's a lot of finesse involved there. You get I feel like neural networks are kind of as much an art as a science at this point, and just like trying different regularization approaches or different sizes of layers and things like that. So I don't really have any wisdom to give you on like how to tune your neural networks if that's what you're looking for. And it's a very open problem out there, I think.
Any other questions? Okay. All right, no more questions. So again, thank you, Dylan, for doing this. We really, really appreciate you, especially being our inaugural Robot Talks presenter.
One quick question. Is any of the software that he's written open source or shareable, or is it all proprietary?
I'm pretty sure it's all proprietary.
Totally understandable.
At one point, we released that graphical editor as like open binary, not open source. But what we didn't release was the actual other side. So like one side of it is the editor, the other side is the interpreter in the robot that actually executes the robot behaviors. And since we never released that, there was sort of not really much point in that. I really think open source initiatives are a great idea, but sometimes depending on your funding structure or it's not practical to do so, unfortunately.
I understand that.
I guess I do have one question of my own on the RoboV. When you first joined it, it showed how it would do the predictability of the consumers. Is it using linear algebra to get all the data then to be able to know where people in a mall are about to go to or anything? Is that the mathematics behind it?
Well, I mean, there's definitely linear algebra involved. So we used a number of techniques there. One of the things is, first we classified each little segment of somebody's trajectory, and for that we used SVM. And SVM, sort of before deep learning became the hot thing to use, SVM was kind of always the top classifier technique, and it's very, very robust and very reliable. So we used SVM for the first level of classification. But then later we're doing things that are not classification, but instead they're like clustering, right? So we were clustering, these are the kinds of behaviors that people do, or these are the kinds of trajectories people take. And for that I believe we used ISO data clustering. It's just a clustering algorithm. But for other stuff we used like k-means clustering. So a lot of these are sort of the classical machine learning techniques that you would learn like in a college course or something. They're not super cutting edge or super, new or anything. And my personal belief is you can really actually go pretty far with standard machine learning techniques. And it's really about getting the right data and coming up with the right, looking for the right thing to learn. And even for the stuff we did with, the camera shop thing, figuring out those clusters, a lot of that was k-means clustering.
So, okay, then any questions? Going once, going twice?
Well, say like Alexa, right? And that's kind of a verbal response logic. How does that kind of knowledge relate to what you're trying to do, or is it?
Your sound just cut out. I think somebody hit mute or something. Hello. Sorry, I still can't hear you.
Okay. Got cut off. All right.
All right. So
most of the question.
How does Alexa relate to what you're trying to do with social interaction? It's kind of trying to do the same thing with responding to keywords. How do you do you leverage any of that, or how does it go hand in hand?
Sure. Yeah. No, that's a good question. It's a very relevant right now because this is a huge booming industry, right? Which is tangentially relevant to what we're doing. Actually, it's deeply relevant. But, there are some important differences. First of all, that's important to keep in mind. So, with things like Alexa and Google Home and whatnot, the turn taking is very, very explicit, right? So, and so is the directionality of the interaction. So basically the way it works is you say a hot word, like a wake word, and then the device wakes up, and then whatever is spoken after that, it captures. And then it knows that that is a command for it to respond to. And then it runs it through its logic, and it does one response. Or I've heard Google Home is actually better and can do multi-turn stuff. But that's very different from like if you're in an unconstrained space and like you have to approach a person and maybe proactively ask them something, or if somebody's talking and you're not sure if they're addressing you. So I think robots that operate in real spaces and in real time like have to deal with a lot more difficulty and ambiguity. I guess another difference is that with things like Alexa, factual correctness is like the most important thing and maybe the only important thing in many cases. Like there's not too much else that it does other than like answer questions or trigger services, things like that. There's a little bit of entertainment content in there, but I think that when you have a face-to-face interaction with a humanoid robot, there's a lot of things that matter, like your facial expression, your body language, your posture, the timing of how you speak, and like your gaze, like who are you looking at and how are you looking at them. especially with like Erica, there's a lot of signals sent through gaze. For example, if she's saying something and then pauses, but she's going to say something more, she'll look away for a bit to signal to you that you're not supposed to take the turn. And then she looks back up and then keeps talking, right? And like all these subtle turn-taking cues are really, really important in face-to-face social interaction. And they are, cleverly sidestepped by these smart speaker type things. So that, again, I think a lot of research and development of these products is about sidestepping some of the hard problems so you can focus on some of the other hard problems. So one of the really, really amazing things that has been achieved by these smart speaker products is speech recognition at a distance and in slightly noisy environments. The state of the art in speech recognition before these things came along was terrible. Basically, you have to have a close talk microphone, or else, the acoustic models and things that everything's trained on are just usually terrible if you're talking from a couple meters away from the phone, maybe the speaker. And these products, these companies put a lot of work, a lot of money into building up corpuses and training these things to do recognition at a distance. So definitely that's the kind of technology that I think can be leveraged immediately with robots.
Quick comment on that. Have you patented any of your work? Because for sure, Google, Amazon, and Microsoft, I'm sure that they are working on visual interaction. The problem is getting over the privacy hurdle. People are concerned.
Wait. So the question is it, have you patented? Is that the question?
Well, not really patented, but aren't you anticipating that Google and Amazon will be implementing visual processing into their products as soon as they can get beyond the public's concern about privacy? Already there are stories about audio, but I can only see.
Okay, hold on. So can you hear the question?
It sounds like part of it's about patenting, part of it's about privacy.
Not really patenting, just the question, don't you foresee that Amazon and Google are probably working on visual interaction so that they can pick up those social cues and make their products better?
Do you think that Google or Amazon are working on visual recognition for
social interaction?
For the social interaction.
Visual
social interaction for their products?
Oh, I'm sure they must be. I mean, I wouldn't call it visual because it's often multimodal and you can use different things for it. But yeah, but that principle, the idea of social understanding and social interaction, I think everybody's working on it. I hope everybody's working on it. And I do have a number of patents. They're mostly Japanese patents that we filed from my previous lab on some of this work. But I think the idea, especially in academia, is it's about sharing ideas and getting those out there because you want other people to use them. You want people to leverage that and build upon it, and we all build upon each other's work to make great robots. Because I think that's what we want. Is we want to see cool robots and cool technology that we're happy to interact with and that makes our lives better, right? So if Apple came out with something that uses I don't know, technologies that I've worked on or whatever, I would still be overjoyed to see that. That would be really cool.
Okay, so then thank you, Dyan. Again, appreciate you doing our first inaugural Robo Talks. It was excellent, and appreciate you taking the time to just speak with us. And I just say thank you, and I give you a round of applause. So thank you.
Thank you. Thanks a lot. Thanks for having me and inviting me for this talk. And I would encourage all of you, stick with the robotics. I know it gets really hard sometimes, but I think it's wonderful that clubs like yours are doing this sort of thing.
Thank you, and thank you very much on this broadcast. And you enjoy the rest of your day. Thank you.
All right. Bye. Bye-bye.